Well, hello, chemistry. Our last video, chapter 8, under quarantine here. So we'll get going. I guess I can breathe better with this. But last installment, chapter 8. Here we go. We're going to talk about net ionic and total ionic equations. And first I wanted to do a little bit of review on the ions. So remember, ions are charged particles. They've gained or lost electrons, so they either have a positive or negative charge. We can have elements that are ions, so metals tend to lose electrons, so they have a positive charge. Nonmetals tend to gain electrons, so they have the negative charge. And don't forget about our polyatomic ions. You have that list of polyatomic ions have a charge, and so that's going to be a key thing. You're going to want to have that list and hold on to that as a reference. Now, we've talked about solubility, and things that are soluble will dissolve, and typically we're talking about stuff that's soluble in water. So we have that rules, the solubility rules. You should have those written down. Having that with your polyatomic ions is a good idea, so you have that as a good reference, because you're going to need to know what is soluble and what is not. Now, when we talk about things dissolving in water, what happens is they get pulled apart, and we've talked about that, and that is called dissociation. When they dissociate, they're getting pulled apart by the water. So when we think about the idea that the water is separating those charges, the ions, out and getting in between them. Now, there's difference when things dissolve. We have an ionic compound like sodium chloride here dissolving. There we go. It's getting pulled apart by the water, and we see the surrounding of the ions. We talked about that. Now, sugar here is a polar molecule itself, just like water is polar. So this is not disassociating. It is not getting pulled apart into ions. It is just polar and mixes with another polar compound. So with those ideas, when we talk about an equation, we have a chemical equation here. This is a complete balanced equation. It's already balanced. And I put the states of matter down here. So we have sodium chloride that is aqueous. It's got sodium. It's always soluble. Chlorides are, most chlorides are soluble except for silver, lead, and mercury. And we have silver nitrate here, which we look at the nitrate side in our rule. It says all nitrates are soluble, so we don't even have to worry about the other part. That is aqueous. Now, what kind of reaction are we going to have here? That's right. It's a double displacement. So when we switch our parts around and we have sodium nitrate, which is definitely soluble, both sides are going to tell you it's soluble, and the silver chloride is our precipitate. Chloride, this is one of the exceptions of the chloride rule, so that is a solid. Now, when we talk about the total ionic equation, we got to think, well, what does it mean to be aqueous? It means that it gets pulled apart by those by the water, and is pulled apart into those ions. So as you see this getting pulled apart into the ions, and I'm showing that by having the charges put here. It's still aqueous. We still need to put the states of matter. The chloride is our negative ion. The silver nitrate gets pulled apart into the positive, the cation of silver, and the anion of nitrate. Now, it's important that we're putting these symbols here. If you had just written Ag with no charge with it, that would be silver metal, not silver ions. So there is a difference. The same with chloride, right? This is not chlorine. Chlorine is a gas, superreactive. Chloride has the charge. So when this gets pulled apart, we're showing that. And the same thing here. If this is aqueous, well, what does that mean? It's disassociated in water. Now, only aqueous stuff does this. If this is a solid, it is not going to disassociate here and is not going to break up. Same if it was a gas. If we had carbon dioxide gas, that was created, well, that's not dissociating either. And if we had water that was made that is a liquid, that would not dissociate either. Only aqueous states of matter will dissociate, and we show it like this. So as we think about the total ionic equation, it's showing how things are broken up. Basically, just think about aqueous. What does it mean to be aqueous? It's pulled apart in water. Now, when we talk about this, we need to talk about spectator ions. Spectator ions are ions that remain aqueous throughout the reaction. So, as we look at our main reaction here and we think back on it, and as we put these in here with sodium, for instance, we look at sodium is aqueous here, and sodium is also aqueous on the other side. So it hasn't done anything. Sodium ions are a spectator ion. Chloride is aqueous here, but over here it's bonded with the silver as a solid. So that has done something different. It's not just aqueous. Silver, the same thing. We had silver ions here, and now we have silver chloride locked up together as our precipitate. We have nitrate ions here, and we also have nitrate ions there. So those are the spectators. The spectators aren't doing anything, right? They're just hanging out. Kind of like spectators at, a football game or whatever. They're not on the field. They're not part of the game. They're just watching. And that's the same with these. So when we better clear that. Talk about the net ionic. The difference with the net is that it doesn't show the spectator ions. So let's go back. It's just showing the main parts. You think of the ones that are actually doing something, kind of like the football analogy there, right? Spectators aren't really doing anything. They're just watching. So here's our original total ionic equation. Now, we think about the spectators. Well, here's the spectator. I'm going to eliminate that. And here's the other spectator. I'm going to eliminate that. So then you think, well, what do we have left over? This is all we have left. Chloride ions and silver ions meet up. They will make a precipitate. That is the net ionic equation. So, as we think about some other examples here. So, here we have two solutions, and we're making a precipitate again. Lead 2 sulfate is one of the exceptions of the sulfate rule, so that is a precipitate. It's insoluble in water. And to balance it, I need to have a 2 there, right? We have 2 potassiums over there. We need 2 here. 2 nitrates, 2 nitrates. Now that also needs to be reflected in the total ionic equation. So when I write the total ionic equation, when this potassium sulfate breaks up, I'm going to have 2 potassium ions floating around. I'm not saying K2 because that would show it being diatomic, and it's not. We have 2 individual potassium ions in solution now. We have 1 sulfate ion with its -2 charge. Again, we don't normally put the 1 with the charges there. We have lead with the +2 charge, and then we have 2 nitrate ions, right, with a -1 charge. When this happens over here, we have 2 of these. Well, that means we have 2 ions of potassium floating around. We also have 2 nitrates, which again balances out. And then we have the lead 2 sulfate, which is our precipitate. So, here's the next part. Let's go on to the net. Well, what do we have to do? We got to get rid of the spectator. Who are the spectators? That's right. Potassium is a spectator. It's aqueous on both sides. And so is nitrate. It's a spectator too. So, what does that leave us with? That leaves us with, and I'm going to rewrite it. I always like to put I guess it doesn't matter. On this side, it doesn't really matter. we have sulfate ions. Again, they're aqueous. We need to show that, what state of matter they are in. And we have lead 2, that is aqueous. And then what is the result? It makes lead 2 sulfate, which is a solid. So that's how you do the net ionic equation. And so remember, when you're doing the total, you do need to represent those numbers, the coefficients, how many there are. So let's try another one. We have potassium nitrate mixing with lithium oxide. And again, you think of our rules. Yeah, nitrates are always soluble, so is potassium. Lithium is an alkali metal. It's always soluble. Oxides are not normally soluble unless they're with an alkali metal. So again, the way those rules work, this is going to be aqueous. Now, we have our double displacement reaction going on. And we see we have lithium nitrate. We're going to have 2, coefficient of 2 out front there to balance everything. And then we have K2O, so it takes 2 potassium, so we've got to have the 2 over there. That also makes the 2 nitrates like this. So when we write the total ionic, whoa, go back. When we have the total ionic equation, we see that, again, I'm showing my appropriate number of things. When this breaks up, those 2 molecules break up in water. I'm going to have 2 potassiums and 2 nitrates. And again, when this breaks up, I got 2 lithiums and then the 1 oxygen. So that should correspond with how the quantity that they have. Now, with this one, who are the spectators? That's right. All of them are spectators. Everybody is still aqueous. So, everybody's a spectator. There's no game going on. There's no players on the field. It's just everybody sitting around watching nothing. This is not even a chemical reaction because nothing new happened. Everything's just still floating around in solution all over the place. Nothing locked up. Nothing new was formed. So, when everything is aqueous, you have all spectators, and it's not a chemical reaction. So, important part. That's one of the big things you're looking for. Look for that stuff. See how it's broken up. Make sure you're doing the correct number quantity-wise with them. So, that's the last little bit of this chapter. We got all these parts. So, now, that's all, folks. You can get cracking on that homework. If you got any questions, get a hold of me, and I'll help you figure this out.